Hi, today we'll be continuing the Java Data Structures video series. We'll be doing a linked deque. So a deque is a double-ended queue, also known as a deque. We'll be implementing it using links. You can add, remove, or view elements from both ends of the queue. So we're going to start with an interface, and we're going to have to create a new linear node because it's doubly linked. I forgot about that, so it has a next and a previous reference. So we'll be doing that, and also it has a head node and a tail node. So all that, it's going to be using all that stuff. So I made this code myself. It's not from a textbook. It's all from myself. So it's not from the Java Foundations textbook. I actually just thought of it myself. So we're just going to be reviewing it. So first we'll start with creating an interface. So it's DEQUE ADT, so deque ADT or deque abstract data type. So public interface deque ADT. Of generic type T. We'll be using generics again, and we'll just quickly do this without the Java doc. So we'll just say public void enqueue front takes a T element, so it enqueues to the front, enquue QUE. Then we'll have public void enquue rear, so we'll enqueue to the rear. So you can add to the front, you can add to the rear, and then we're going to have to be able to remove from the front and the rear. So deque front, no parameters. Whoops, forgot void here. Actually, yeah, that is void. Technically, I probably should have returned something. Thinking about that now, I probably should have returned T, but that's okay. I guess when I did it, I didn't really think of that, but that's fine. You don't have to, again, do that. My professor never took marks off for that when I did void. It's up to you. But it's good to return a reference if you can. So public void deque rear. So you can remove from the front or the rear. And then you can check the front element. So front. And then you can check the rear element as well. And then the same normal methods is empty, which is a boolean, size, which is an int, and toString. So that's it. We have it all. We'll go to our linear node class, so we're going to have to create a new linear node class that just doesn't have a next reference but also has a previous reference as well. Object reference variable. So we're going to have to create our node class here. So public class linear node of generic type T. Actually, I was going to call it doubly node, but I already coded it. This is a longer one. So we'll just redo our linear node class for now. So public T linear node of generic type T. So that's going to have some instance data field. So private T element, private linear node of generic type T. Excuse me, called previous, and then a private linear node of generic type T next. Then here we'll create the constructor, the first constructor, public linear node that creates an empty linear node. We'll say this dot element points to null. This dot previous points to null, and this dot next points to null as well. So all, which they are all null right now, but we're just setting it to null just to show that it is null and just to make it clear. So then here we'll create an overloaded constructor. We'll say public linear node, and then we'll pass a t element as parameter. And we'll say this dot element points to element. This dot previous is null, and the next is null as well. So I haven't done this in a while. I haven't looked at this code in a while, so this is just like a first timer. Feels like a first timer, but we'll get through it. So then we'll do some getters and setters here. So public linear node of generic type t, get next, and then we'll just return this dot next. You don't have to do this. You can just return next. That's fine. We'll just do it this way. Actually, personally, I don't really like doing that. We'll just return that since we don't have to use this. So here we'll say public linear node of generic type t, and get previous, the get previous method. Excuse me. So we'll return previous. Why is this one yellow and this one not? That's okay. So public linear node of generic type t, get next, return next, public linear node of generic type t, get previous, return previous. Okay, we forgot one here, so we'll do public void set next, takes a parameter linear node of generic type t node. We'll say this dot next points to node. So get next, set next, get previous, and then set previous. So public linear node. Actually, no, we already did that one. Get previous. So public void set previous. Takes a linear node of generic type t node. We'll say this dot previous points to node. Then here we'll do public t get element. Then we'll return element. Then we'll do public void set element. T element. So all this stuff you're going to be using for a long time. If we're going to be doing Android too, or learning about Android. Personally, Android can be good, but the thing is, it's only good for one. The setback is it's only good for one operating system, which is Android. It's not good for Apple. So something that would be better would be more of a cross-platform language such as React Native, that lets you write one code for Android, iOS, and you can even make a web app with it. But I guess it does help to learn. Does help to learn as much as you know, I guess. it is personally Java is an older language, so I guess it's only good for Android at this point, but it is still helpful because they use a lot of the same concepts. So anyways, we'll talk about that later. So then here we'll just say this dot element points to element. But at least in Android, just on that note, you do learn XML, and you can use XML in React Native, so it is slightly helpful. But again, it uses JavaScript, so it's different. A React JavaScript. So we'll be learning about that like in a long time later, so we have a lot of stuff to do till then. Not that long, but after HTML, CSS, and JavaScript, so that's going to be in 1, 2, at least 3 video series later. Maybe not that far, but actually, well, yeah, until JavaScript. So one of those, it'll be at least the 4th video series until we even get to React, so we'll be working on that a long time later, but don't worry, it is coming. So after that we'll just check. So public void set element t element, public t get element, public void set previous, public void set next. Sorry, public void set previous, public void get previous, public void set next, and public void get next. So that's all fine. Then we'll just go back to our link deck class, or if I haven't explained that, we have a class called link deck. I've created a new class. I've just wrote public class link deck of generic type t. And then that's it. Then here we'll just start creating our instance data for our link deck. Sorry, I've just misplaced my file here, so let me just go back and open it. Okay, so again, this is code. I wrote it myself, so it's not from the textbook or any other textbook or anything. So we'll just implement here the deck ADT of generic type t. And I apologize, these video series don't take that long to make. Maybe a couple weeks at the most, but the problem is uploading the videos. Like, sometimes it takes like an hour just to upload one. So it can, especially if they're like an hour long. This one's already 13, okay, not that much, but yeah, it can take a while, so I'm trying to do at least, 2 a week. If I have like 15 videos, that could take a while, right? So I will try to get them up. So now we will create some instance fields here, instance data. So they'll be private. So we'll create some object reference variables here. So private linear node. That's just telling us to implement the methods. Yeah. Okay. So private linear node of generic type t head. Private linear node of generic type t tail. Private int count. So we're gonna have a counter variable, a head object reference variable, and a tail object reference variable. I think we used these already. Excuse me. We use head, and then tail we used in the queue, linked queue. So here we'll create the constructor, public linked, not linear, linked deck. So count is set to 0. Head points to null, tail points to null. And again, a lot of these concepts are in C as well, so we'll be doing the C series after this with Android, and there'll be a little bit of Linux stuff too. So constructor for empty deck, count set to 0, head and tail to null. Public void enq rear, so we'll do the enq rear method. We'll pass in t element. So here we'll create a new linear node of generic type t. Node points to new linear node of generic type t. We'll pass in element. We'll say if head is equal to null and tail is equal to null. Whoops. So if head is equal to null, I'll just space these out, and tail is equal to null. So if both head and tail are equal to null, that means it's empty. You can also check, we could have also written here if is empty, but I just wanted to do that to make sure, I guess. We'll set head to point to node, and tail to point to node as well, so at the first element, head and tail are going to be both pointing to the same memory location. And then we'll increment count by 1. So it's easy as that. So if head is equal to null and tail is equal to null, head points to the first element that the first node that we just created. Tail does the same, and we increment count by 1 because now we have one element in the deck. But if it's not empty, then we'll say else linear node of generic type t. We'll call it temp node points to head. So I traversed using head, but we really could have just used tail and did it the way that in the queue example, the textbook way, they just do a tail and they shift it. Looking back at what I wrote now, it might be a little less efficient because tail, well, I guess we do have to set previous, so maybe not necessarily. But we can come back and think about that later. We'll just do this for now. So while temp node dot get next does not equal to null, so we're going to just traverse the old school way from the head node. Then temp node points to temp node dot get next. So while temp node dot get next is not equal to null, temp node equals to the next element. Then once it gets to the one that's not null, then we'll set node. We'll say node dot set your previous element to we'll say here we'll say node set your previous reference to temp node. So node's previous reference is set to temp node, and temp node's next reference is going to be set to node. So again, the code works, it's just maybe we could have made some more efficient modifications. So then we'll say tail points to node. count plus plus. So what's happening here is we got this part. If it's empty, then set your head to the node, tail to the node, count plus plus. Then L if it's not empty, then else linear node temp node points to head. While temp node dot get next is not equal to null, or the head dot get next is not equal to null. Temp node points to temp node dot get next. So traverse. So let's just make an example here. We have 5, 6, and 11. Okay, let's say we have 5 and 6. So if head equals to null and tail equals to null, well, does head equal to null and does tail equal to null? Head equal to null, false. Does tail equal to null? Also false, because they have elements stored in the memory location. So then we'll hit the else clause. Then here we'll create a temp node pointer. We'll point it to head. While temp node dot get next. So we'll say while temp node. So while head dot get next is not equal to null. While temp node, or while temp node that's pointing to head. So while temp node dot get next is not equal to null. Temp node equals to temp node dot get next. So here right now this is temp node. So while temp node dot get next does not equal to null, so 6 is its next. Temp node points to temp node dot get next, so temp node points to temp node dot get next. So now this is temp node. So then we'll say node dot set your previous. So then we'll check if back to the loop. We'll say, well, temp node dot get next is not equal to null. Well, it does. The next is null because there's no more elements. Then we'll say this will get false, so it'll come down to this bracket underneath. Then it'll say node dot set previous. Node dot set previous reference to temp node. So it's going to say, okay, set a previous reference to take node and set your previous reference to temp node. So we have our node here, and what we're trying to add is 11. Actually, where are we? Over here. Let's just say we're trying to add 11 here. So we still have that element. We still traversed. So we're right here. So node set your previous reference to temp node. Sorry. So we'll change. Let's just say this is null and node's floating out here, and it's not linked. Let's put like a. Let's just say it's floating out here. So this is the node we're trying to add. Everything's fine. We just have linear node, temp node, pointing to head. Then we traverse get next is not equal to null. Temp node points to temp node dot get next. So now temp node's this. So it's saying, okay, sorry, I got a little confused here for a sec. So then now it says node set your previous reference to temp node. So it's like, okay, take this spot, take null out of here and set a link like that. Well, let's just say the comma is a link just to keep it the same. So we'll say, okay, node set your previous reference to temp node, and it's saying, okay, temp node set a previous set your next reference to node. So now they're doubly linked. There's a link like this and a link like this. Something like that. Like you can imagine a link at the top like this, and or actually like equal sign. Like there's a link at the top that's previous and a link at the bottom that's next. So the one at the or let's say the top is next and the bottom's previous. So node.set previous is under there pointing to temp node, and then temp node, which is 6, has a next reference pointing to node, which is 11. So just an example. So then it sets tail to point to node. So now this one's also tail, and then 5 is head. But the other way we could have did this is the way that the queue did it, is where they set tail to point to. They took, I think we took tail and we pointed it to the node. I'm just trying to think if we could have done that as well. We had a tail reference. And we use the head to point to, and we use the tail to point to the last element. So we checked if it was empty. Then if it wasn't empty, we took tail and, we set its next reference to node. Okay. We took its. So if we were to take tail and set its next ref, so if tail was originally 6, right? We took its next reference to point to tail. We took it, so if tail was 6, then we could have taken temp 6, which was tail, and pointed it to this node 11. Then we could have said node, set your reference to tail, and then we could have set tail to point to node, if that makes sense. So I'll just what we could have done here. We could have said tail.set next to node. So tail so the original tail, which was 6, set your next to node, and then we could have taken node, set your previous to tail, and then we could have said tail points to node. That might have worked. It might have been more efficient and would have ended up with possibly a 0, an O of, we'll get into this in the next few videos, but big O notation, so big O of 1 time complexity, O of 1, because we're just shifting tail by 1, whereas the implementation that we have here, this loop is an O of n. Needs a comment, so it's a big O of n. Is that a big O? Yeah, it is. Big O of n time complexity. So that means that it's going, however many elements there are in this traversal. So if there's like 5, then it's O of 5 time complexity, whereas this one, it's always going to be O of 1, so it's constant. Did I say it was constant? So the O of 1 is constant. We'll go over all this after. And then O of n, I think that's linear. I kind of forgot. But anyways, you should just know that this one's it's less efficient, because if your computer was to process 1,000,000 elements, or if it had like a list or like a linked, if it had 1,000,000 links, it could take like a few minutes to do that, or even longer. Whereas an O of 1 shift could just take a second or less, like a millisecond, or whatever, a fraction of a millisecond. So overall, this implementation would save memory. It would be faster. Your program would run faster. If this one worked. So we'd have to test it and see. But if that one works, we can change it and see it at the end if it works. So anyways, this way, I've already tested it, it works, so we'll just go with that for now. There's always a few different ways to do it, and you can always make it more efficient. But we'll just go back to the other method. So we'll have I think this is NQ front. No, this is NQ rear, so we'll NQ front now. It's pretty much the same thing. But I think I'm gonna make this a two-part video because this could take a while. So I'll just do the next one. Because if we do all the methods in this video and debug, I have a feeling it's gonna take a while. Maybe even an hour and a half or longer. So we'll just do this method, the next one. So we'll do, we'll say public void. Actually, not DQ, sorry. We'll do, okay, so public void, yeah, NQ front. T element. So then we'll say, so we're going to add an element to the front of the queue. What we're really doing is just creating a new head. Unless the elements are null. Okay, let's just see what we have here. So linear node of generic type T. Node, so we'll create a node. Points to new linear node of generic type T. We'll pass an element. We'll say if head. So it's the same thing, if head equals to null and tail equals to null. Then we'll set head to node, tail to node, and count plus plus. And we'll say else. Okay, so this time we're not setting our node to point to head. I'm not sure why I did this, but I'll find out in a sec. So linear node of generic type T. It's funny when you're looking at your code that you wrote, you're like, well, I did this, why did I do that? So we'll have linear node temp node point to tail. And I think above we pointed it to head. So that's why I'm wondering why. Well, we'll find out here. So we'll say while temp node dot previous. Okay, so we're traversing backwards. Does not equal to null. I feel like there's like 4 different ways to do the same thing. Above was an example how we could have used the tail, and I feel like we could just use the head here. So anyways, we'll just say while temp node dot get, did I say get no I didn't, get previous with a capital P does not equal to null. Not minus, does not equal to null. Why is this? Okay, so that's fine. So we'll say temp node points to temp node dot get previous. So we're traversing backwards, I guess. Then node dot set next. Why would I do that if head was already? at the head element. So node.set next to node. So we're adding to the front. I feel like there's more different ways to do this. So anyways, what I have here is node.set next to temp node. Node.set. So take the node that we're trying to add and set its next reference to point to the head. Okay, that kind of makes sense. Then temp node, set your previous to point to node, head point to node, count ++. Okay, it makes sense, but it just seems like there's a better way to do that. So can we have just said node dot set next to head set previous to node? Wouldn't that have worked? So can we just said instead of this, can we have just said what did I just say? So node dot set your next to head. Then after that we could have said head dot set your previous to node, and then head points to node. Would that have worked? Instead of, it would have been more efficient, right, than traversing again. Same thing kind of above. This way it works. It's just like, can we make it better? Can we make it faster, right? So node dot set your next reference. So the node that we're trying to add, let's just say, what do we have? 5, 6, 11. Let's just say we're adding 13. Then we're saying, okay, so create a, whoops, let's just say that the node here is 13. Let's just say we're trying to add a node here, it's 13. So then here we'll say node, set your next to point to head, and head, set your previous to node. Set your next to point to head, and head set your previous to node. It seems like it could work. It should work. And then it's saying head, okay, reset and point to node. It should work. We can try it after. But I will take a break and I'll see you in the next part, which this will probably be compiled, so it's just gonna say on to the next method.